So this is the video about the testing of the bad ear using high-speed camera and syncing that frame rate of high-speed camera with the data we get from the Nylon coil sensors. And it's similar to the one video I did before. And here you can see on the left is the voltage and the frame rates plot of the Nylon coil sensor. And then at the right side is the bad ear and showing the current frame here, which is at frame 1, and it's about 879 frames in this whole clip. And since my computer isn't capable of handling this many frames, I will be manually moving to one frame to another. I might be skipping some of them, but the data is here, and if there's a powerful computer which is good enough to do this, you guys can use that. But here, so what my findings are, basically we're gonna start at frame 1 here, and right now the actuator is pretty much at atmospheric pressure, like it has no pressure. And as I will start to move from here to here, you will start seeing some pressure will build in this chamber. So I'm going to go from 1 to 205. Like I said, it's 205 right here, so it'd be right at this point. So 205, and when I hit enter, you will see this inflating a little bit. You can see that it moved a little bit, and which caused this voltage to increase, because when the actuator inflated, the sensor actually stretched and the voltage increased because the resistance decreased when it stretches, and it's still in that linear region, like from the testing data from Instron, which showed the sensor is a linear in the very beginning of the stretch, and then it kind of turns to a non-linear section. And now here we'll see a large drop in voltage, which kind of shows that it comes to a non-linear section here, because the voltage is dropping, the resistance is increasing, and it's from 212 from 205. And let's see what happens if I go to 212 from 205. You will see, you kind of see it. So 205, you will see this whole actuator inflating again. I'm going to show you 212. The inflation was pretty quick here, and it was larger than from 1 to 205, and which probably have stretched the sensor to its nonlinear region, because the sensor, the way it's placed in at the back of the ear is the ear has a similar structure as we have for the base of the actuators. And then the sensor is placed inside that base, and the silicone is poured into the base, and then the actuator, the top part of the actuator, only the chamber section, is put on the ear and let it cure. So basically the sensor and the actuator are cured at the same time. And now after that, after this much stretch, the sensor will start to increase the voltage again from 212 to 222, and we'll see what happens. So as I go from 212 to 222, the actuator actually inflated with a larger magnitude than it did for any of these, and which actually increased the voltage, and the resistance has decreased. And the voltage still starts to increase up to this point, but it's pretty noisy here. So I'll kind of go frame by frame, but it might be twitchy because of my computer is not that powerful enough. But you can kind of see what's going on here. It kind of bends to a certain point, and you will see it might be like when it's bending, it might be up to here, it starts to go back to that non-linear region again, and then it starts to drop the voltage. Or it might be doing it right here as well. I'm not 100% sure at this point for this section yet. I might have to do more testing at a higher sampling rate. And what you will also see is it starts to move in a forward direction, and which might be, and the pressure inside the actuator is decreasing when it's still in the same region, and which will make sense this voltage going down, because the resistance will increase because the sensor is now unstretching, and this part might be dead. And now about at this point the voltage will decrease more, the resistance will increase, and it's unstretching right now, which makes sense, but we can kind of see it unstretched more than it ever did up to this point, and the voltage decreases a lot. And this could be another reason this to be happening is maybe the sensor is getting gripped by the silicon and actually getting stretched into the nonlinear section more, and which causes this big drop. But after this point, the sensor will tends to increase the voltage again, and this might be due to coming back to the rest position, like right here, and then getting stretched when it's going into the backward direction. But since the sensor is placed inside the actuator, I'm not sure how much of this is affected in going backward direction. And now we get into this zigzag kind of or noisy region, but it's still increasing the resistance at a lower rate. Decreasing resistance at a lower rate, increasing the voltage. And you might be able to see that zigzag. Oh no, you can't. Let's try again. Alright, let's see. It's actually moving only in the backward direction here. It starts to go in. It starts to actually open up more. You can see that a little bit. It's hard to see it when it's processing slowly. Kind of does that, and it's coming back to the original rest position again, which might be due to, which is also shown here. And after 416, it does as a larger going up and down, and then it starts to dissipate, and then about at this point again it starts to inflate the actuator again, and you can see that happening there. So this data like this is similar. It kind of shows the same thing for rest of the cycle, but we did about 5 trials of this sensor data and got the sensor data, and every time there was a next trial there was a baseline shift, and each trial was about 5 minutes apart, and but the baseline shift, the rate of change of baseline shift decreased as it was moving for a longer time, and it started to show some conversions, but I haven't seen a really close conversion like getting the same data. We might have to run that ear for a longer time to see if that happens, and also to see if another issue we have to handle is also to see how to keep the sensor in the linear section and without going to that or the parabolic part like we saw on the Instron. Kind of like if I draw with the mouse, it kind of goes like this and it does that. And that's pretty much it. And there are more other ears with different setup, but the size of the actuator is same. Size of the sensor is same for that ear, and we might be seeing same type of effect in that. But I will look into the data and then see. We'll go from there, and I will put in the photo of the back of the ear, the way the actuator was put in the email for this video link. So thank you for watching.